For decades, artificial intelligence operated exclusively as a passive oracle. The system sat idle, requiring a human prompt to execute a single action. The generative models that recently dominated the industry share a specific architectural limitation. They function as stateless, single-turn request and response mechanisms. Generating a flawless block of Python code within a web-based chat interface is a solved problem. Independently investigating, debugging, and resolving a live infrastructure incident requires a completely different cognitive architecture. Closing that operational gap requires transitioning large language models away from isolated text synthesis. They must be re-architected into functional, autonomous computing engines. Scaling intelligence across an enterprise demands continuous execution loops. A workflow cannot scale if the software stalls every time it needs human intervention to determine the next logical step. This agentic model operates in direct contrast to traditional robotic process automation, or RPA. RPA relies on deterministic fragility. It follows rigid if-this, then-that heuristics. When a script encounters an unexpected user interface change or an unhandled exception, execution halts completely. Agentic AI introduces probabilistic resilience. When an agent encounters a failure, it reads the error trace, adjusts its reasoning, and attempts a new solution to achieve autonomous recovery. In practice, this means an agent can receive a high CPU utilization alert from a Kubernetes cluster, query the Datadog API for telemetry, parse Elasticsearch logs for anomalous stack traces, and execute a pod restart, entirely without a human in the loop. AI has moved past suggesting theoretical solutions. These systems execute and verify them directly in production environments. This architecture relies on the large language model serving as the central controller, or the brain of the system. That an LLM is inherently a stateless system. To function autonomously, it must be embedded within an orchestration layer that dictates strict state management. The very first requirement is short-term memory. This is maintained through in-context learning, allowing the agent to track the history of its current execution thread and remember tool outputs from previous steps. The second major requirement is long-term memory, which retrieves historical data, past interactions, and documentation. Long-term memory is achieved by converting data into dense numerical vectors. The agent then performs a semantic similarity search, using a vector database like Pinecone or pgvector, to retrieve exactly the context it needs. Equipping the model with persistent memory reconfigures the static text predictor into a context-aware entity, ready for sustained, long-running operations. To bridge memory to action, the agent utilizes the REACT framework, a cycle of reasoning and acting. Before executing any command, it traces logic internally, asking, what is the current state? What is the goal? And which tool gets me closer to that state? Those tools are known as actuators. They are the functional endpoints the agent uses to manipulate its digital environment. Through a process called tool binding, engineers provide the LLM with the exact schema of a Python function or REST API. The LLM parses its environment and outputs perfectly formatted, structured data, like JSON or XML, to deterministically trigger these external tools. This tight, continuous interplay between probabilistic reasoning and deterministic tool execution provides the mechanical engine for true autonomy. Taking this theoretical architecture and deploying it into live distributed production environments reveals specific engineering hurdles. The first major risk is the infinite loop. If an agent hallucinates incorrect arguments for a specific tool, it can enter a continuous cycle of failing and retrying, leading to massive, unbound API consumption. Engineers mitigate this by implementing strict maximum iteration limits and hard system timeouts, preventing resource exhaustion before it cascades. The second major risk is context degradation. As agents generate massive amounts of intermediate logging data, they experience a lost-in-the-middle phenomenon, where the model forgets its original objective. Maintaining reasoning integrity over long sessions requires semantic routing and hierarchical memory summaries to compress data without losing fidelity. Finally, granting an autonomous agent access to execute SQL queries or bash commands opens a direct attack vector. A malicious prompt injection could command a database agent to execute a drop table command. Securing these systems requires sandboxing operations within ephemeral Docker containers and strictly enforcing the principle of least privilege across all active API keys. An autonomous agentic system is only as viable and only as valuable as the engineering guardrails containing it. Solving the local engineering hurdles immediately exposes the macro-level strategic challenge: scaling these systems securely across an entire enterprise. Organizations face the transformation paradox. Individual technical capability is soaring as developers build complex agents, but enterprise operating models are lagging heavily behind. This chart plots individual capability against organizational readiness. A small fraction operate in the frontier zone, where advanced AI skills meet corporate infrastructure. Many sit in the blocked agency zone, highly skilled engineers with robust workflows, but lacking the systemic support to deploy them. The data shows that organizational infrastructure, culture, management practices, and governance accounts for more than twice the reported AI impact of individual effort alone. Empowering individual engineers with autonomous tools produces no enterprise value if the operating model is too fragile to securely absorb their output. Manually approving a single bad output from a localized chatbot is manageable. Deploying unsupervised agents to execute workflows at scale compounds organizational risk exponentially. To manage this, enterprise IT and security must become the active control plane for agent operations. They must treat agents as managed entities, with distinct identities, strict permissions, and rigorous lifecycle management. The infrastructure must be designed to capture localized agent telemetry across the network. The system needs constant visibility into what worked, what failed, and exactly where operational outcomes drifted. Capturing these signals and encoding them into shared routines builds owned intelligence, institutional know-how that compounds over time and cannot be replicated by competitors. Agentic AI integrates these continuous data streams to re-engineer the entire enterprise into a self-reinforcing, autonomous learning system. For the last 2 years, artificial intelligence has largely functioned as a passive text generator. Today, that same basic architecture is rapidly evolving into active problem-solving systems capable of orchestrating their own workflows. Think of a standard large language model as a brain in a jar. It possesses a massive amount of information, but lacks a physical way to interact with the world. An AI agent is that same brain, equipped with a specific mandate and the tools to carry it out. 4 distinct capabilities define this shift. First, the agent perceives its environment, such as a database or an inbox. Second, it decomposes a high-level goal into a sequence of subtasks. Third, it selects and uses external tools. And fourth, it executes those tasks autonomously, updating its own state until the objective is met. This shift means AI no longer requires a human to prompt every micro-decision. You define the goal, and the agent determines the necessary steps to reach it in the real world. Leveraging this autonomy creates a fundamental tension. The more independent a system becomes, the more vulnerable your operations are to its errors. This chart plots AI autonomy against operational risk. Moving from a single prompt to a complex multi-agent workflow creates massive efficiency gains, but the risk profile follows a similar trajectory. Operating in this top right quadrant introduces severe architectural overhead. You are delegating authority over your APIs, databases, and customer interactions to software that functions without constant human oversight. The primary risk here is an autonomous hallucination. If a standard chatbot makes a mistake, a human reads a flawed sentence. If an agent hallucinates, it acts on that incorrect logic, potentially sending an unauthorized email or deleting critical data before anyone can intervene. To utilize this technology effectively, you have to select the precise level of autonomy a task requires. Calibrate it incorrectly, and you risk exposing your operations to cascading, expensive failures. To prevent those failures, agents use reasoning frameworks. These structured logic sequences stop the model from guessing blindly when faced with complex problems. The standard approach is chain of thought. The AI is forced to write out its intermediate steps to solve a problem. Because the reasoning tokens become part of the context for the next step, the model effectively debugs its own logic in real time. For more strategic problems, we use tree of thoughts. Instead of a single path, the model explores multiple branching possibilities simultaneously, self-evaluating each one and backtracking if it hits a dead end. This framework can solve highly complex puzzles, but it is computationally expensive. Each branch requires multiple LLM calls, quickly driving up your operating costs. When an agent needs to interact with the world, it uses the react loop, reason plus act. The agent forms a thought, takes an action, like a search or an API call, observes the result, and then updates its internal logic to determine the next step. Without strict monitoring, React agents can get stuck in repetitive loops. If an external tool returns an error, the agent might try the same failed action indefinitely, burning through your API budget without producing a result. Choosing a reasoning framework is a balance between deep strategic capability and the financial risk of runaway compute. An agent's ability to act depends on tool calling. This is the mechanism where the AI admits it lacks information and generates a structured instruction for external software to provide it. Consider a complex travel request involving two partners. The agent first calls a flight API to find options for the traveler departing from London. It cross-references this data with a second API query for the traveler departing from New York, looking for a logistical match. The agent autonomously overlaps these arrivals in Japan, filtering through live pricing to find a solution that works for both travelers simultaneously. It then calls weather and transit APIs to route the rest of the trip through the mountains, identifying where bus reservations are mandatory and checking if the weather will permit hiking. However, giving an AI access to external software creates a massive security risk called prompt injection. Malicious instructions can trick an agent into executing destructive commands, like deleting files it was only supposed to summarize. Agents also utilize long-term memory through vector databases to store your preferences. While this enables personalization, every piece of stored memory the agent has to retrieve adds significant latency to its response time. Unlocking this utility requires strict permission scoping. Without a policy of least privilege, giving an agent hands and a memory can lead to catastrophic security breaches. Once you establish the tools, you must decide on the architecture, a single highly complex agent or a team of specialized agents working together. Multi-agent systems reduce hallucinations by separating roles. A researcher agent gathers data, while a separate reviewer agent checks that data for errors. These agents cross-validate each other's work before the task is considered complete. Deployment usually happens through orchestration frameworks. LangGraph uses node-based state machines, allowing you to maintain fine-grained control over how data moves between different agents. Contrast this with Crew AI, which organizes agents using human-like roles. You assign specific goals and backstories to agents like manager or researcher, making the system easier to build and manage. The fundamental trade-off here is the massive infrastructure overhead. Because these agents must communicate and review each other, a single task requires multiple LLM calls, creating significant latency and higher compute costs. You also need specialized agent-to-agent communication protocols to ensure all these separate modules remain synchronized throughout a complex workflow. Multi-agent systems trade simplicity for extreme reliability. They are unnecessary for basic tasks, but they are mandatory for high-stakes enterprise operations. Understanding these internal mechanics is the first step toward deployment. Now, we have to match these specific architectures to your individual requirements. For individual prosumers or consumers, custom development is often overkill. The most efficient path is using specialized wrappers like Stardrift that handle the integration for you. These platforms deliver hyper-personalized itineraries and live bookings in minutes, providing the benefits of an agent without managing underlying code or APIs. The trade-off here is financial. You pay a premium subscription for a polished interface built on the exact same APIs you could connect yourself. For small businesses, the best ROI comes from deploying single React agents into defined, high-volume workflows, such as customer support or automated data entry. This approach generates massive labor-equivalent output, but it requires a human-in-the-loop fallback. AI success rates drop significantly on tasks that take longer than 4 hours, so human oversight remains a non-negotiable requirement. Enterprise builders face the most complex requirements. They must develop custom, multi-agent networks supported by long-term vector memory for deep data engineering. At this scale, the architecture must handle millions of real-time data points securely, where a single autonomous error could lead to significant financial loss. This necessity forces a heavy investment in agent ops infrastructure and rigorous defenses against prompt injection to keep the entire network secure. This master framework matches each tier to its ideal setup. Consumers use wrappers. SMBs deploy single agents. Enterprises build custom multi-agent networks. Crucially, note the governance row. Required human oversight scales directly with the complexity and autonomy of your system. Agentic AI exists as a spectrum of architectural choices. Every increase in system capability requires a corresponding, deliberate investment in human control. Today's workforce is navigating a transition on the scale of the Industrial Revolution. It is a shift happening fast enough that trying to track every new tool can feel like a full-time job. The World Economic Forum estimates that by 2030, artificial intelligence and related trends will displace 92 million jobs. But displacement is only half the story. Those same trends are expected to create 170 million new jobs. That leaves a net gain of 78 million opportunities for those positioned to take them. AI itself isn't going to walk into your office and pack up your desk. The risk comes from professionals who learn to use these tools to outpace your current output. When 80% of HR leaders say the workforce will be a hybrid of humans and digital labor within 5 years, neutrality stops being a safe option. To remain relevant, you have to decide which side of that equation you want to occupy. You hear the command to learn AI every day. The problem is, that advice lacks a practical roadmap. It doesn't tell you what to do when you sit at your computer on Monday morning. We can simplify the noise into 2 actionable paths. Path 1 is the total pivot. This involves stepping away from your current career track to occupy newly invented, dedicated AI roles. Path 2 is the AI upgrade. You maintain your current industry expertise, but rewire your daily workflow to incorporate digital labor. Framing this transition as a choice between building systems or directing them cuts through the hype. It clarifies exactly where you need to invest your limited learning hours. Let's look at Path 1. Corporate budgets are shifting rapidly to fund entirely new tech departments and new job titles. Choosing the total pivot requires intensive technical upskilling. You are looking at rigorous study in systems deployment, cybersecurity, or ethical AI governance. We are talking about roles like an AI orchestrator who conducts disparate agents to work together, or an AI cybersecurity specialist defending networks against automated malware. Over half of CEOs are hiring for AI roles that did not exist a year ago. If you qualify, you gain an immediate advantage in a market where the talent pool is still incredibly shallow. But the trade-off is a lack of stability. There is no established career roadmap here, and the technical requirements evolve monthly. The total pivot is for professionals who have a high tolerance for ambiguity and are willing to reskill on a constant loop. For most knowledge and creative workers, the calculus is different. Take graphic design as an example, where AI is already handling routine, repetitive tasks like image cropping and font selection. The AI upgrade doesn't require learning to code. The focus here is mastering industry-specific tools to automate the repetitive parts of your job. Delegating layout generation or data sorting to an agent frees up hours of your week. Your value shifts from manual execution toward creative strategy and managing client relationships. The hidden trade-off is intense competition. As automation makes basic production easier, you must surrender your attachment to the manual craft to avoid being undercut. Succeeding in the upgrade path requires checking your ego. You move from a role of manual production to one of directing and auditing digital labor. This matrix shows distinct focus and inputs, technical infrastructure versus industry-specific tools. Outcomes also differ. First mover advantage versus a productivity boost. But notice the common ground. Both paths rely on human skills AI cannot replicate: emotional intelligence, adaptability, and complex problem solving. You also need agent literacy. This is the universal ability to effectively collaborate with and prompt AI assistants to get accurate, ethical results. The time of coasting on a single degree is over. Continuous, baseline learning is now the minimum requirement for economic survival. Within 5 years, most workplaces will operate as a hybrid of human and digital labor. You have to decide where you fit in that mix. If you are highly adaptable, tech-literate, and crave the high ROI of an early adopter, you are the opportunistic pivoter. Choose Path 1. If you deeply value your current industry expertise, but need a defensive strategy against automation, you are the time-poor knowledge worker. Path 2 is your route. Identifying your personal risk tolerance and your attachment to your current role is the only way to pick the correct path and avoid burnout. It is normal to feel anxious about these changes, but you can navigate this by shifting your mindset from "how will AI take my job?" to "how can AI help me grow in my role?" Here is your immediate micro-action. Pick exactly one AI tool relevant to your chosen path and learn its basics this week. Both paths carry risks, but doing nothing guarantees your skills will become obsolete. Mastering a collaborative partnership with digital labor is the most reliable way to maintain economic relevance as these systems scale. Right now, artificial intelligence is like this glowing energy core, immensely powerful, but trapped inside a confined glass cube. We have built brilliant language models, but they all live inside a chat window, waiting for us to type the first word. That is the core limitation of our current technology. It has no independent initiative. It doesn't wake up in the morning and decide to solve a problem on its own. It only acts when prompted, and it only executes the exact parameters of that instruction. It's an incredibly sophisticated tool, but it is not a teammate. So despite having access to nearly all of human knowledge, modern AI remains a passive oracle. If a human isn't sitting at the keyboard, constantly turning the crank, the machine just stops working entirely. To get high-value work out of these models, we have to act as the bridge. This is why prompt engineering is a mandatory skill. It is the meticulous, labor-intensive process of feeding AI exactly what it needs to hear. Take a look at this diagram showing a technique called few-shot prompting. You can't just drop raw text data into the model. You have to manually feed it 3 or 4 specific example blocks so it learns the exact output format you want. Or consider chain of thought prompting, where the output expands into this branching flowchart. Here, we are forcing the AI to show its work, mapping out a step-by-step logical pathway so it doesn't hallucinate the final calculation. To clear that execution bottleneck, we need a new class of artificial intelligence. We need AI agents, systems designed to actually use tools and accomplish goals on their own. We are moving away from static text generation bots and toward dynamic software capable of altering its environment. It's the digital equivalent of breaking through the screen to turn the mechanical gears directly. To see how this works in practice, look at a recent case study from a global consumer goods company. Their marketing team needed to optimize ad spend across several different media platforms. In the baseline human era, pulling the data, analyzing the metrics, and manually applying the budget shifts required a team of 6 analysts working for an entire week. AI agents bypass this heavy manual workflow entirely. They do this by plugging the AI's reasoning engine directly into the company's enterprise software. This diagram outlines how that connection is driven by the observe, plan, act cycle. First, in the observe phase, the central agent node extends connections directly to the company's pipelines, continuously gathering data and retaining context. Next, the plan phase. The agent uses a reasoning engine to evaluate metrics against goals, figuring out exactly what needs to be done. Finally, the act phase. Once approved, the agent automatically updates external media platforms with the exact recommendations. By utilizing this cycle, that marketing project dropped from a 6-person, week-long grind to just one human and one agent finishing the job in under an hour. The observe, plan, act cycle takes AI from an isolated thinking tool and turns it into an active, high-performing teammate that directly drives business outcomes. Look at this structural model to see how this shifts entire enterprise architectures. We move from large pyramids of human workers and dissolve into a hub-and-spoke model, small central human hubs managing expansive networks of AI agents. This shift allows organizations to scale their operations and handle significantly higher volumes of work without being tethered to a proportional increase in human headcount. These agents will collaborate with humans while simultaneously delegating tasks to other specialized AI agents to solve cross-departmental problems in real time. The definition of enterprise work is changing. We are decoupling the physical limits of human labor from the speed of company growth. As agents gain the ability to deploy applications and run tests through simple instructions, the traditional barriers to managing complex systems are lowering. For many departments, plain language goal setting is becoming a viable alternative to writing rigid, custom code for every new task. The worker's responsibility evolves. Instead of executing the data pull, your job is to define the strategic goals, stress test the agent's recommendations, and ensure your AI teammates uphold privacy and ethical standards. In the near future, your professional success will not depend on your ability to execute repetitive tasks. It will depend entirely on your ability to manage the machines that manage themselves.
Recently, Taylor Swift filed a series of legal trademarks with a very specific goal: protecting the exact sound and character of her voice from unauthorized AI impersonations. We are seeing artists, lawmakers, and corporations scrambling to build legal walls around human identity. But while we focus on protecting our own digital faces and voices, we are missing a much deeper systemic vulnerability. The autonomous AI systems we are plugging into our networks currently lack a fundamental security requirement: a verifiable digital identity. As these systems transition from passive tools to independent actors, the security of our digital infrastructure hinges on our ability to assign them a verifiable identity. To understand why, you have to look at how the technology is evolving. We are moving past passive chatbots that only speak when prompted. Enter agentic AI, systems engineered to run continuous, multi-step workflows entirely on their own. Take modern agriculture. You now have autonomous hardware out in the orchards that continuously analyzes soil conditions, adjusts its own settings, and decides exactly when and where to spray chemicals, with zero human input required. In healthcare, similar agents are working behind the scenes, reading patient data, booking follow-up appointments, and coordinating complex care schedules across hospital departments. We are granting these independent actors direct control over our physical and digital systems. This creates a systemic blind spot because our security protocols were built exclusively to authenticate human users. For years, cybersecurity has operated like a medieval castle. You build a massive wall around your network to keep the bad actors out. But AI agents bypass the wall completely because they are deployed directly inside the perimeter. This internal access opens up highly specific vulnerabilities. The first is prompt injection. This is when an attacker slips malicious instructions into the data the agent is processing, tricking the system into breaking its own rules and leaking sensitive information. Then there is shadow AI. Employees constantly deploy their own unvetted, undocumented productivity bots to help with their daily tasks. These invisible agents operate completely off the radar of IT teams, processing company data with zero official oversight. Even sanctioned agents suffer from over-permissioning. A developer might spin up an AI to organize a single spreadsheet, but inadvertently granted administrative access across every connected system. If that single agent is compromised, the whole network is exposed. Our current identity and access management protocols rely on human speed passwords and manual reviews, but an autonomous agent can retrieve, process, and expose thousands of sensitive records across multiple third-party models before a security admin even blinks. If we want to safely harness the power of these autonomous systems, we have to stop treating them like simple software features. We need to manage them as digital employees. That starts with establishing first-class identities.
Every single agent must be issued a unique, verifiable cryptographic ID badge, creating a permanent paper trail for every action it takes. Next, we apply the principle of zero trust through microsegmentation. We divide the network into isolated vaults. An AI designed to schedule interviews for HR is physically walled off from accessing the company's financial databases. Finally, we have to eliminate standing passwords. Instead, we use just-in-time access. Agents receive short-lived cryptographic credentials that exist only for the exact duration of their specific task and vanish the millisecond that task is complete. Together, these elements form the architecture of non-human identity.
It's the only structural method we have to hold a machine strictly accountable for its behavior. Looking ahead to 2030, the global volume of data is projected to multiply tenfold. The vast majority of that will be unstructured data, emails, videos, audio logs. AI agents will be the only viable mechanism capable of sorting, reading, and processing that sheer volume of information. We are entering a high-stakes environment where deeply personal information, from your private financial records to your medical scans, must be handled flawlessly. In this landscape, a company's competitive advantage won't be the fact that they use artificial intelligence. It will be their ability to mathematically prove that their AI is strictly governed, secure, and contained. As our digital spaces flood with autonomous actors, authenticity and verifiable trust will become the ultimate premium currency in the market. The next decade promises a significant increase in productivity. We are looking at a system where AI seamlessly farms our food, manages our health, and orchestrates our global logistics. But we cannot safely maintain these complex autonomous systems without addressing the fundamental security gap they introduce. Autonomy without accountability is just chaos. To survive the AI age, we must give the ghost in the machine an identity.